Welcome. This lesson will focus on what we call refraction analysis in flat irons. Refraction analysis, by refraction analysis, I mean we are going to take a set of first breaks. As you see, we have our shot record here picked. And if I bounce around the survey on the map here, you'll see that I have pretty consistently picked these shots. So now we're going to take these traces, these picks on these traces, and perform refraction analysis. And by that I mean I'm going to compute refractor velocities and delay times. We consider that a trace pick for a given refractor comprises the delay time at the shot, a delay time at the receiver, and a linear move-out term, which of course embeds the refractor velocity. So we're going to take this set of picks and we're going to assign a set of these picks to a refractor and then analyze those picks for that refractor and compute refractor velocities and delay times. Then we will also look for possible geometry problems. So this will not only involve computation, but it's also going to involve the QC of the solution. So the first thing we need to do once we have a set of picks is we need to assign these picks to a refractor. So I'm going to go under delay time here, and we're going to go to branch assignment using picks. And these five blue dots here on this map over here on the left are places where I've already done refractor assignment. So I'm going to clear those, and we're going to start from scratch here. And I'll just click here, and I'm going to set 5 of them, one in each corner of the survey and one roughly in the middle. And we have 3 refractors on this data set. We have one refractor here that's about 5,700 feet per second. We have another one here. You can see the change in slope, and it's about 6,000 to 6,100. And then we have a faster one over here, and it ranges roughly about between 6,800 and 7,100 feet per second. So I'm going to focus on the middle one because it's the best behaved for the survey. This inner one actually turns out in practice is pretty inconsistent. So if I try to compute a solution on that, I'll find that I have lots of problems in different parts of the survey. So anyway, so I'm going to focus on this, and I'm only going to do a single layer solution. And I'm doing 4 things when I set this refractor assignment here. See, I'm setting a velocity. Can you see the number on the velocity here? And you'll see the delay time's changing also. And the extent, the left to right extent here are actual distances. So I'm setting a minimum distance of 1877 and a maximum distance of about 4,800. Okay, so I'm going to set that velocity there. And I've applied a linear move out. It doesn't matter what the linear move out is, but I prefer to actually use a linear move out that's close to the velocity that I'm actually picking, just because it helps my ability to differentiate between subtle refractor changes. So for example, if I turned off the linear move out, it's very difficult to see those changes in the refractor velocity. But when I apply it, it's much more obvious. And these are actually fairly subtle changes in velocity compared to some surveys. So let's do, and then the other thing that's happening is I'm computing a delay time here. So and the way I'm doing that is that, let me just project, I'll just do this backwards, and you'll see that by projecting over here to 0 offset, if you look at the axis up here, you'll see there's my distance. So there's 0 offset. So if I project this back to 0 offset, this line, you'll see that it comes out to be about 37 milliseconds. That's because it's intersecting here at 74 milliseconds, and half of that is 37. A delay time is half of an intercept time. So I'm setting refractor velocity, delay time, minimum and maximum. Now, we don't necessarily need to use these delay times and velocities, but it is a good way of to see how consistent we're being. So anyway, so let me do this, and I'll set 4 more. So I'll set one over here. Let me apply the linear move out. And you can see, again, this is pretty inconsistent here. I'm going to do a limited offset range here. Let's do over here, better behaved. By the way, the northeast section of this survey is the worst behaved. And then here's the southwest, and like I said before, I'm going to do one in the middle. And these are interpolated values, obviously. So As you can see, we're getting pretty close anyway. And and then over here, we can actually look at how consistent we are. So we can look at the velocity, refractive velocity, and we're pretty consistent here. We're going from 6,000 to 6,100. So if these are feet per second. So if this was meters per second, this would be a range of 30 meters per second. So this is pretty tight. So we were very consistent. And then down here, let's look at delay times, which are the intercept time, half intercept times, like I said. And they're ranging from about 39 probably to about 47, 48. So again, we're talking about a 10 millisecond change. You can see that the refractor is going to be deeper over here, and it's going to be shallower up here, and then in the middle, it's going to be pretty close to the middle of our delay time range by coincidence. So we're going to apply changes down here in the lower left, apply changes. Do we want to interpolate those? Yes, let's interpolate them. When we interpolate them, what happens is by interpolate, we mean we're going to interpolate those to the shot and receiver locations in the database. So what I'm going to do after this, as soon as I exit this, I want you to remember the shapes here, because I'm going to show you in the database that this is exactly what we're starting with. So I don't want to kill picks. And let's not do this yet. And under here, under database, let's just look at one of the tables here. Let's look at the receiver table. And I'm going to do a cross plot, and I'm going to do easting versus northing. So I'm going to look at a map view, and I'm going to look at the delay times. Delay time one here, and then plot. And let me shrink this down a little bit so we can see it clearer. So you can see we have red up here, blue over here, and then green. Okay, so we've interpolated that value to these receivers, and if we looked at the shots, we'd see the same thing. Or another way we could look at this would be to look at the let's see here, the model building window. And you can see if we look at delay times down here, right now it's plotting elevations. Let's look at delay time 1. Again, here we see that those values interpolated to the shot receivers in our database. So this is what we're starting from. The program will work just as well if we start from 0, but sometimes we might want to actually look at this and use this information. So for example, if I want to go to my pick window, for example, now, I can bring up a pick window. Here's our pick window. I can actually apply the solution. So I can, if I go over here, I can apply shifts. And so I'm going to add here under model analysis, delay time shifts. I can apply those. And then I'm going to lock my axis. And I can also limit by branch assignment. Okay, so a perfect solution, at this point, I might even have a perfect solution. I don't, but it's conceivable that I possibly could. A perfect solution would flatten these picks right on 0. And as you can see right there, I'm pretty close. Now if I bounce around over here, you can see not too bad, not too bad. In general, I'm actually doing pretty well. Okay, so I'm close to 0. But also you can see that there's an awful lot of places where I'm not. So let's just leave this shot up, and then let's do our delay time analysis. So under delay time analysis, I could have accepted that assignment or that option to go right into analysis, but that would have taken me directly to let's see here, where was it? Analysis. This sequence here, and this sequence is a combination of velocity, delay time, velocity, delay time. So it's going to iterate on velocities and delay times. So let's do that. And it's already applied the solution, but as you can see, it's already as you can see, a lot of that detail that you saw before is now removed, and we're pretty close to 0.
You're gonna call it.
Anyway, let's look at some other shots around here, here. Okay, so we've applied velocities and delay times. If we go up under that model building window here, we can look at our solution. So here's our delay times. Let's replot this. So this was the original delay times. And I'm going to, let's look at the refractor. These are the velocities, the delay times that we set when we computed from the branch assignment. How do I refresh?
There's a reload plot button somewhere.
Oh, there it is. Okay, so this is our new delay times that we've computed from the picks themselves.
I've got to go see Chris. I'll just see you there, okay?
Okay. See.
Well, it'll be fine.
Then that was, so now let's look at the velocities and the refractor delay time velocity. And then this is the velocity field we just computed. And you can see the range is 6100 to 6160. So pretty close to what we had before, but these are actually computed from the pick times. Then, so now let's look at the diagnostic, one of the diagnostics that we have here. One of the diagnostics is the average pick, the pick error itself. But as you can see, we don't have any of that information here. So we need to reload this plot, reload this scale here, and now we have all this information. And the delay time error is a very diagnostic plot. This tells us how well the program liked the solution. So you can see, like, where it's blue, it should be pretty flat on 0. But where it's not blue, for example, some of these red points here, we're going to zoom in on those. So let me zoom in on this one. Let's have a look at this guy. Now this guy was not picked very well. And the reason it wasn't picked very well is we were doing some kind of pick prediction before. But as you can see, we missed it because by automatically picking it, this actually has a geometry error in it. So watch these vectors up here in the upper left. I'm going to pick this thing better. And you'll see that there is a very systematic error here. And this is probably more like this. Okay, so now, as you can see, this is somewhat chaotic. I have a few mispicks here, but I'm going to do something else here before I go any further. I'm going to display these traces by azimuth. So this looks pretty confusing, but as you can see, there's a real systematic error in the program. The algorithm thinks that this shot belongs down to the southeast of where it is. Here's where the shot is, and it says, no, I belong to the southeast, quite a distance. So I'm going to about 630 feet, or about 200 meters. So let's look at this axis here, and let's plot by azimuth. And now you can see what looked like chaotic behavior is actually quite systematic when we're looking radially. So here, for example, if I roll across here, if you look at that vector over here, you'll see that I'm looking on a very smooth, I'm just looking around me. So we can clean up these picks very easily. And in fact, you can see this would be a much easier domain or orientation within which to pick the picks to begin with. And now I'm going to move to suggested location. And now I'm going to, let's clean up some of these. And let's apply it again. And one more time. Here's an error here. All I have to do is click on there to remove that. And we're pretty close to where we need to be. So we've moved, and this is where the shot came from originally, and now here it is. So you can see that it really belonged to the end of this shot line here. We could do the same thing over here. We could click on here, and let's move to suggested location, and then we'll clean up the picks, move again, and you can see this shot moved from here over to here. Here's another one. Again, I'm going to move. Get rid of that mispick, and I'm within 1 foot. Okay, so what I've done, we could go, there's several more geometry errors in here, but at this point, so what we did, again to review, we did refractor assignment, we computed refractive velocities and delay times, we computed delay times for the single refractor, so we did a sequence of the velocities and delay times, and then we looked at some geometry problems, and we looked at the average pick error. Now related, this error is just how much around 0, what's the deviation around 0. So if I added some mispicks here, so a lot of these problems are not necessarily just geometry problems, they might actually be mispicks. In this case, most of them are geometry. Here's a question here, like looks like some inconsistent picking. So this isn't necessarily a geometry problem, even though up here these vectors might look like they are. So you have to be careful. Don't just consider every time these vectors say I belong someplace else, like in here saying I think I'm off by 40 feet. It's not necessarily the case that it is. It could just be inconsistent picking, or the refractor itself becomes inconsistent. We picked it as best we can, but still, and the way the solution is for that refractor just might have implied that it's geometry when indeed it isn't. So you have to be very careful, and that's one of the reasons why we don't just say, "Hey, automatically change all the shots to minimize the error," because mispicking can manifest itself like geometry. Okay, so that's the end of this talk. Thank you very much.